So thank you, Professor Sitabra Sinha, Dr. Anindya Chakraborty, Dr. Shoresh Das for inviting us, and thank you for the warm hospitality and all the arrangements that you've made. It's a great pleasure giving a talk here. I'll be talking about financial markets as evolving complex systems because this is part of this conference series which takes the economy as a complex system. And I'll be dealing mainly in the correlations of price movements and co-movements, correlations and co-movements in the price time series. Most of the work I've done in collaboration with my PhD student, Kiran Sharma, Onindo, and some of the recent work that I've been doing with a group of Thomas Seligman and François Lebras at UNAM in Mexico, along with postdocs Hirdesh and Rakesh. I have been doing work for a very long time, so I will show some of this work which I had done long time back with my master's student, Jukka-Pekka Onnela, Professor Kimmo Kaski, Professor János Kertész. Also my former students, Gayatri Tilak, Esteban, Tamás, and Remy at École Centrale. Some of the students which were working with Onindo, Shreyans and Balagopal. And I must thank Fabrizio and Matteo for discussions which helped in this work which we are doing now. So basically the objectives of the talk is studying correlations and co-movements of stock prices, and basically study the changes in the correlation patterns, and if we can define some sort of a state in a financial stock market. Before I wanted to study the economy as a evolving system, I thought I'll tell you a few words about my evolution in the field. Because I've been basically doing a random walk, not only on space, on the surface of the Earth, but also hopping between fields. So I thought I'll spend a few slides on that. I was born in Darjeeling, of course, a very beautiful city. It's a small town actually, and no pollution, unlike in Delhi, and very pristine weather. So I went to these schools, again very old and very beautiful schools, Catholic schools and Protestant schools respectively. Then I came to Scottish Church College in Calcutta and studied in the University Science College for my master's. Then I did my PhD with Professor Vikas Chakraborty at Shah Institute of Nuclear Physics, and I finished my PhD in 2002. Then I moved actually to Finland for my postdoc, and followed by a 2-year period at the Brookhaven National Lab, which was famous for its accelerator physics. Then I came to India as a lecturer in theoretical physics at the Banaras Hindu University, and this is one of the largest universities in India, like a city built in the shape, university built in the shape of a rising sun, and these are the rays coming out from the central office. It was a very beautiful place, but then I was offered a position by Professor Frederica Bergel at École Centrale. So there I spent 5 years along with Frederic and Damia, who were sitting in the audience. And then I was offered a permanent position again in JNU, and basically to start the field of complex systems. So 2014 onwards, I've been in JNU. So that's what I've been hopping around, and now I'm at the School of Integrative Sciences, which deals with complex systems. And amongst many of my interests is, of course, econophysics, social physics, time series analysis, combinatorial optimization, ab initio calculations in condensed matter physics, quantum physics and entanglement. And I've begun doing experimental nanoscience for the last 3 years and published a few papers. This is basically my small group in JNU. This talk will be basically on econophysics, as this is a conference on evolving systems. And with one of my sociologist friend in JNU, we actually wrote an article at the invitation of Onindo and Sitabra. Can an interdisciplinary field contribute to one of the parent disciplines from which it emerged? And that is what the conference was dedicated to. Can economics be a physical science? So we gave our own perspective. And this was actually an outcome of the discussions with my sociologist friend, Dhruv Raina. And those who are interested can please have a look at this article. Actually, I will not be able to dwell much on this article right now. So in complex systems, like the way I see it is that, physicists have been dealing with many particle systems for a very long time. So any physical object would have almost 10 to the power of 23 molecules, which is a huge number. But then luckily what happens is that each of these molecules are identical. And also perhaps the interactions among those molecules are known. So we know, the interactions that are present amongst matter, so the forces which take part. Now in a complex systems, what we see is, first of all, each of these constituent particles are very different, and they can differ in their nature, their properties, their behavior, and also the interactions are diverse and not known. So, and what happens in typical social relations is that I cannot even model the interaction well, and so to find something in aggregate, which we typically do in physics, we write down a Hamiltonian and then we have a prescription to find all the properties of the system. Those simple tools cannot be used directly in the field of complex systems. And of course, so people have been studying complex systems from different perspectives, and people have studied the neural networks, and of course that the brain is a very complex structure. So if you study one neuron in isolation, you cannot tell anything about the brain because it's a really complex form which has taken place from many such of the order of, I think, 10 to the power of 6 neurons. Similarly, if you study one ant in isolation, you cannot talk about the collective behavior of ants, and then ants are known to be very social insects, and you cannot explain the formation of anthill or any social behavior amongst the insects. Similarly, if you study one car, you cannot explain the formation of traffic jams, but that we know is like a emergent property that comes out of this system of cars. So often what we find is that the way they are arranged in a network also becomes very important, and many of you know and come from computational biology, systems biology. I can see my friend Arijit also here. He's, I think, starting the computational biology along with Shitaprata in this school, in this institution. So they would agree that in terms of number of genes, the human beings has only 3 times more that of a housefly. But in terms of complexity, we can they are not even scalable or comparable. And so the way the genes are arranged, or the transcription regulation takes place. So this is from the transcription regulatory network. You can see that the complexity is much greater. So often people, especially coming from physics, study the networks and then try to measure complexity. And I think that's what Tiziana was also trying to do. And we follow a similar route in financial time series as well. So financial market can be treated as a model complex system because there are many agents which are interacting to perform the collective task of finding the best asset price. And so you can, this is what attracts physicists, because you have collective behavior of agents and you try to find out, can we say something about these systems? And what we observe are basically time series prices. You can also find other more details in a limit order book. And so if you just go and search in Google, you can find different types of time series of stocks, and you often find also this is in French, but okay. So limit order books, you can see the levels at which prices are being put, and you can follow it over time. So what you get is basically a whole time series. This is a daily time series for General Electric for a period of almost 20 years. And then mostly economists or us, we are interested in the logarithmic, daily logarithmic returns or other type of price returns. Now, in terms of time series, people have studied random time series very long. Physicists have been studying chaotic time series. The econometricians have Arch and Arch models, which Shorish was mentioning a while ago. And then we have the financial time series, which is the real time series. And you can see that it's very complex compared to any of these. And many of the properties cannot be actually explained by any single model. And so in terms of dynamical systems, this is very interesting to physicists because this is a new type of complex dynamical system which we cannot understand or model very well. And so there was a wonderful article by Hamakon in 2001 which talked about stylized facts that have been formulated using general qualitative properties of asset returns. And so you could find such things like, properties which I think Niels was also mentioning. And it's found in almost all the assets, independent of the type of economy you're looking at, the type of market you're looking at, the type of stocks you're looking at. Then these type of properties do hold for everybody. We had another review article in 2011 along with my colleagues Federica Bergel, Ioan Emunitoke, and Marco Patriarca, and where we had more recent data, including high-frequency intraday returns. And if you want, you can again have a look at this paper. So I will focus my talk, this one, especially on analysis of correlations and co-movements. So if you're given a time series of different stocks, you would be constructing, taking a time window and finding the return matrix, and then you would be shifting this return matrix to see the evolution of the stocks. And often what we do is we look at the equal time cross correlation. So this is between company I and J, and this is how the cross correlation coefficient is defined, and these always lie between -1 and +1. So if you plot the cross correlation coefficients over time, so you would see that, okay, this is varying from 1998 to 1984 to 1996, and you can see how the cross correlation coefficients are distributed. And this was during the 1987 Black Monday crash. So as soon as the data sets actually hit the 1987 Black Monday crash, you can see that the properties of this distribution changes drastically. Now, if you look at intraday data, you will see certain patterns also evolving. And for example, if you look at the volatilities amongst the stocks, so this is between 10 o'clock and 4 o'clock in the evening, and 5-minute bins, so there are 72 bins. You'll see that the markets are more volatile when they open and more volatile when they close, and they have this U-shape thing. We also studied the variance between the stock prices. So in one of them is the variance, the other one is the volatility. And whether it is 5-minute interval or 1-minute interval, you often see the same types of things. And this is when the London Stock Exchange opens actually. So you see a reflection in the CAC 40. This is when the New York Stock Exchange opens. Again, you see it in the CAC 40. So you can see that the markets are correlated, and one market influences the other. If you look at the cross correlation matrix, and then you look at the eigenvalues of that matrix, you will see that the maximum eigenvalue, which actually captures the mean correlation coefficient, it fluctuates, but there is a steady trend. So when the markets open and when the markets close, there is actually an increasing trend. So the markets become more correlated towards the end of the day. And so these type of properties, so this is what I was saying, that the maximum eigenvalue actually captures the average correlation. So you can see how closely the two things are correlated. And you see that there is an increasing trend of the average market correlation in the every day. So we used to look at these patterns, and so when you are actually formulating strategies or doing trading, you have to keep these things in mind, that the volatilities are changing, the correlations are changing. So often you should choose your portfolio of stocks accordingly with these things. So you build a strategy which takes into account these things. Now we had a different way of approaching and looking at the correlation patterns also. So what you do is, since you have the correlation coefficients which will lie between -1 and +1, you give them a nonlinear transformation using this one. And this was first proposed by Rosario Mantegna long back in 1999. And then we exploited this thing in 2002, 2003, a series of papers with my collaborators. So you give this transformation, you convert them into distances, and then what you do is you draw a minimum spanning tree. So what happens is, if you look at the distance elements, it's just a nonlinear transformation of the correlation coefficients, and this is how it looks. Now what you do is you build a minimum spanning tree, and you look at the elements which are in the minimum spanning tree, and you will find that you've selected n-1 elements from this entire spectrum. So you're not looking at most correlated or most shortest distance elements, but over the spectrum, entire spectrum. And so what you get is something like a tree like this, and the way we draw it is that the highest vertex degree, the node which has the highest number of connections, is put at the center, and this is General Electric actually. and then you draw the tree like this. So these symbols are given from the business sectors classified by Forbes, and you will see that all the energy companies happen to be in one branch, all the utility companies happen to be at the other branch, because this is a hierarchical way of clustering. Now, of course, it doesn't match exactly, because the way Forbes classifies it and the way we have done is very different, because we start with price time series and nothing else, and then look at the cross correlations and arrive at this one. But what is interesting is that if you see the evolution of these trees over time, then you'll see that the topology changes very much. And so during a normal business day, the market is much more, it has distinct clusters or distinct sectors, and you can see that the topology is very different from around a crash group topology. During a crash, it is well known that the market becomes very correlated. So you will see that the colors change, which was the significance of the amount of correlation, because we were plotting the distances. So if the distance is short, then it's much more correlated. And if the distances are high, then it is less correlated or more anti-correlated. And so you'll see that the change in color is one, but also the change in topology. And so you can see that, the market, there is a different amount of complexity involved in the market. And I think that is what Tiziana was also looking at, but from a very different perspective, I think. And so if you look at, for example, the degree distribution of these networks, so how the degrees of each of these nodes are, you can see that there is a change in the topology, which is reflected by the degree distribution. And so you can follow the difference in the complexity of the market by looking at the degree distribution or other properties of these networks. One interesting application testing which we did is, suppose you do a Markowitz portfolio optimization and you find out that which are the stocks that appear in your Markowitz portfolio. And then you look at the weights of these different stocks. Of course, during this, we took 110 stocks over a period of these 20 years, and you'll find these weights differ. And there will be certain companies, so for this one, which always appears in your portfolio. And there will be certain stocks, for example, General Electric, which will never appear in your portfolio. And that's quite understandable, because General Electric is a big conglomerate, and this is the position it was holding, and it has strong correlations with many companies. And so if you do a Markowitz portfolio optimization, it will not appear in your portfolio, because if the price of General Electric goes down, it will drive the entire market down. And so what you see is that you can follow these weights and then track which are the companies that you should invest, or which are the companies in your portfolio and where are they located in the tree. And then you'll find that the ones which are in your portfolio are never towards the center, because those are the ones which are very highly correlated and correlated with many other companies. So, and these are the ones which are safe to actually invest. So in your portfolio, these are the ones which will appear more frequently. Then we wanted to see the evolution of the market as if like a geometrical map. And one of the tools that the computer scientists use is like multidimensional scaling. So what this algorithm does is, if you give it a distance matrix, an input distance matrix, for example, this is between 10 cities in the United States, so Atlanta, Chicago, Denver, Houston, Los Angeles, Miami, New York, San Francisco, Seattle, and Washington, D.C., and you know all the distances between them. So this is the input metric, and then it will give you a map of coordinates. So it will give you a set of coordinates which will satisfy that distance matrix. Now, the problem is that you are giving a distance and you get a set of coordinates. But now, obviously, this set of coordinates is not unique, because you give a translation or you give a rotation to the set of coordinates, it will still satisfy the distance matrix. So when you're looking at the evolution, you have to be slightly more careful. So as I was saying, that if you just change it a bit, the distance matrix is still similar. Now, what we wanted to do is we wanted to start from the return matrix, calculate the cross correlations like before, convert it into the distance using the same distance transformation, and then use the multidimensional scaling to get these coordinates for the maps. And then use the k-means clustering to find the cluster among the different maps. So we wanted to try with synthetic data which we produce and also with the empirical data, and the next few slides I will show those results. So first synthetic results, and there what we wanted to do was I generated myself 60 assets, and every 200 time steps the correlation among these 60 assets change. And how I did it was basically these 60 assets, I created 4 clusters of 15 companies. So I know the amount of correlation between these 15 companies, and I generate it artificially, and I change it every 200 time steps. So initially I put a 0.35 amount of correlation between all these assets. So there are 4 clusters, and the correlation is extremely high between these time series. Then I reduce that correlation, and you see that these start spreading. Okay, I reduce it further, and you see that approaching together. And when it is like 0.05 or it's almost no correlation, all of them fall into one. These colors are the ones which I've put initially, so which show that this belonged to that cluster. But basically, it has become one cluster of uniformly random distributed dots. Okay, so what it shows is that as soon as the correlation structure changes, you can see that in the evolution of the map. So you'll see that when there are distinct clusters, that means the sectors are anti-correlated to each other but correlated amongst themselves. You will see them distinct points like these. And when the correlation reduces or becomes highly correlated, so all of them are behaving together, then you'll see them approaching together, and it will be like one cluster. So you can see this, use this algorithm to see the evolution of the market. So now I try it with real empirical data, and so we've chosen 18 companies' daily price returns, and these are the parameters. And I don't know if you can see, but I can read. So you'll see that all the French banks are in this thing. So this is BNP, AXA, Crédit Agricole. These are all the European banks, Deutsche Bank and all that. And then these are anti-correlated to the American banks, JP Morgan and Bank of America. Then you'll see also these are the European cars, so BMW, Peugeot, Fiat, Renault, and these are anti-correlated to Toyota and Nissan. And then Volkswagen is very different from the rest of them. And so what we could do is, this is a graphical user interface made by my students. You can change the dates, and it will show you how the market evolves over a whole period of 5 to 10 years, depending on what returns you get. And you will see very interesting things. For example, you will see that Exxon and Chevron are always paired together, and they move around together. Similarly, you will see Pepsi and Coca-Cola always move around together. Similarly, JP Morgan and Bank of America always move together. Now, if you look up in Wikipedia what is pair trade, you'll find exactly this. And this was a strategy which Morgan Stanley used in the 80s and made millions of money. You'll see that this is the Coca-Cola and Pepsi, Exxon and Chevron. These are pairs which people try to identify. Now, if you give a time series and a whole lot of time series, it is very difficult to find these pairs because what you get is always numbers. But these methods of visualization easily enable you to identify, because you can just follow the map and you can identify, which are the companies which are moving together. And then you can easily identify and then exploit the pair trading strategy, which people often do. We also followed the subprime crisis, and this is with the CAC 40 in France. So before the crisis, Lehman Brothers, you could see that it is in the center of the market. And then I make several time shots. I'm presenting only 3. You'll see that Lehman Brothers goes out, and after the crisis, the Lehman Brothers is behaving extremely different from the rest of the market. So you can actually see or trace the movements of each of these companies. So if you want, I can just repeat it. So before the crisis, it was here. Then during the crisis and after the crisis. So you can trace the movement of each of these stocks and see how they move. Okay. You have a question? Urgent one? No, we're just following the data which they historically. Yeah, it was there actually still. Yeah. Now, as Tijana was showing, what I could do also is study these correlation matrices over time and see for the changes in the correlation patterns. Now, this is what there was a nice paper in Scientific Reports by Munich, Shimada, Schaffer, Levraz, Thomas Seligman, Thomas Goore, and Gene Stanley. They looked at these correlation patterns and they tried to identify that are there patterns which are occurring more commonly than by chance, and then can I use these patterns to detect some sort of a market state. So they used their own algorithms and they found that there are commonly 8 states that they could identify, and that was reported in the scientific reports. We found that their method is quite nice, but we didn't agree with the results and the approach, so we followed independently. And what we did is, of course, like I showed you before, I can look at the correlation coefficients and the distributions evolving over time, and I can also look at this is the mean correlation coefficient evolving over time. So there will be certain frames which will be extremely correlated. This is above 0.8. This is frame 34, which is this one, and this happens to be the 2008-9 period when there was this Lehman Brothers crash. Now, you will see that these are some of these patterns that you are seeing. And what we do is we look at the similarity between these correlation matrices. So I take this correlation matrix and I measure the similarity with another correlation matrix, this and this, or this and this. So what I do is I define a similarity matrix, which is nothing but the element-wise difference in the cross-correlation coefficients, and then take an ensemble average over all these cross-correlations. And you'll see that this is the similarity matrix that you're getting. And from here, in fact, you can make out when the crisis actually happened. So this was the Black Monday crash in October 87. This was the dot-com bubble. This was the Lehman Brothers. This was the credit crunch. This was the Euro debt crisis. So you can see through the similarity matrix these major crashes. And then what we do is we take all these frames. So we have basically 200-day window, and we have a 8,000 time series. So we have basically 40 frames. We use the multidimensional scaling to plot them in as coordinates. What we do is we look at the ratio between the inter-cluster, intra-cluster distance. So you look at these, you can, the problem which Tiziana was saying, that people often, give an ad hoc that, okay, there are 8 clusters or 6 clusters or 4 clusters, and you don't know how many clusters there exist. So what you do is you actually vary this number of clusters, and then you look at the inter-cluster ratio, and then the minimum one actually gives you the optimum. So in this case, it is like 6, and then you divide this into 6 clusters, and you see that, okay, oh, this is falling quite well. So this is cluster, how these things are looking at. And you'll see that, okay, this correlation matrix is basically the one which we had, and this indicates some sort of a critical behavior when the market was crashing. This is also very highly correlated, less correlation, it goes down in this direction. So what is happening is that if I look at this mean correlation over time, what it does is effectively puts these thresholds, and then you'll find that frame 34 was in this market state, and these 4 matrices were in this market state. So what Thomas Seligman and the group had done, we basically showed that, okay, this is basically like effectively putting these different thresholds and dividing into market states. Now within each market state, now you can look at the properties of the cross-correlation coefficients and look at their structures through multidimensional scaling or other network tools like Tiziana is looking, and they find different types of complexity. So this is what we are doing now. I also wanted to show briefly the work which we were doing with Onindo, and that is within the market. Now I look at the different sectors. And you'll see that if you do a multidimensional scaling in the Indian Bombay Stock Exchange market, so the sugar industry is separate, but the rest of them form a big bulk here and a big bulk here. And what we find is that the sectors are very mixed up in the Indian market, and which is reflected also in the minimum spanning tree or any other type of hierarchical clustering method. But when you look at the market indices, so you have the sectoral indices, and you then do a multidimensional scaling or a MST, then you get to find there is more systematics. So what we did, we started with the Bombay Stock Exchange, and then we have more results in this recent scientific reports paper, where we have dealt 65 sectors from 27 different countries and found the minimum spanning trees. And using the eigenvector subtlety measure, we also found which are the core and which are the peripheral sectors. And we did that for 27 different countries. Here only 20 countries are shown, and you can see that the sectoral maps or networks are very different from each country. But there are similarities between certain countries like this, or between these two, or between these. And what we did is we followed which are the sectors that are in the core or in the periphery, and you'll see that finance and this is the industrial sector, these are always at the core, whereas you have TC, which is always in the periphery. So you look at the sectoral movements in each of these countries over time, and you can also compare it for each of these countries. And you can see, for example, during 2008-9, IT was quite doing well, but then 2015-16, after the subprime crisis, it hit, and it has become less important. So you can look at the sectors and their evolution actually. So that is what we have done. So now I just wanted to point out some general references. So the first part of the work, you can find these several series of articles in these conference proceedings, a few in the last proceedings that we had. This is the book which we wrote with Frederic, and if you want to look at the results of limited order books, you can look at this book. And if you want to look at the individual papers, you can find them from my website actually. And I will be organizing the meeting in JNU and Delhi University along with Nivedita, which is going to start from Wednesday. And I hope to see most of you in that conference. And so thank you for your attention, and if you have any questions, I'd be